Another type of transport that we might be familiar with, both seeing in the environment and experiencing in our own bodies, is a thermal gradient, which is two locations that have two very different temperatures. And this is why in the winter time, if you leave the front door open, you may have had a parent that yelled at you, "You're letting all the heat out." And they were actually right. So heat, which is defined as the movement of molecules, heat usually flows from hot to cold. And we can see that sometimes when cold weather comes in on the Finger Lakes. We can see some of the hot dissipating into the cold. Fog is an example of this as well. Cold air is coming into hot land, and we're getting some of that dissipating heat. We also know about this for ourselves with this example over here on the left, which is that if you build up heat in your body, which you do every day, I mean, we maintain 98.6, but if you build up a little bit of heat, that heat will dissipate out from your hot body into the cooler air around it. Now, if you're in a hot tub that's over 98.6, that's not going to happen. And later in the semester, we will talk about why it is that drinking alcohol and maintaining in a hot tub over your body temperature prevents this dissipation of the thermal gradient, and thus can cause death at the very extreme. A thermal gradient, though, if we were in a physics class, it would have a broader definition, and we would define it as areas of molecule movement. And heat is not the only thing that can determine that. Most often in this class, we will encounter concentration gradients. And a concentration gradient is defined as two areas of high and low concentration. In this picture up here on the right, is a picture we should get used to. This that I'm outlining is a cell. And over here, this is the outside environment of the cell over on the left-hand side. And these little molecules here, these hexagons, are actually glucose. It's the common shape that we use for glucose. And we can see over here on the left that this is a very high concentration of glucose outside of the cell. And if we were in a chem class, we would use the brackets as an abbreviation for concentration. So high concentration outside of the cell, low concentration inside of the cell, and all of these molecules want to rush to the area of low concentration, much like you at a movie theater where you see lots of people sitting. You rush to another area where no one is sitting, and they'll continue to do that until there is something called equilibrium on both sides of the cell. Right? Because equilibrium is a set point that the movement of the molecules is trying to achieve. Why do I have a luscious cup of coffee here? Because the smell of coffee or a citrus fruit or anything that your nose can pick up, the smell is molecules dissipating into the air. And of course, the closer you get to the coffee, the more molecules there are, and you can smell it. But over time, these molecules will move out from an area where lots of them are, over the coffee cup, to an area where very few of them are. Unfortunately, the same goes for carbon dioxide in soda, which is why it always goes flat. There are also things known as pressure gradients. And I think you're getting the hang of this here. But water, blood, molecules, they like to flow from an area of high pressure to an area of low pressure. And usually in situations with a pressure gradient, usually, but not always, usually there is a physical pump. And this right here, let me draw it more accurately for you. This right here is the heart, and it is the physical pump that moves blood throughout your blood vessels. And so what the heart does is it contracts, forcing or pumping blood into your blood vessels. Now, all the way down here at your toes, the pressure is very, very low because you're very, very far from the pump. Up here in the aorta, which is the big vessel that leaves the heart, there is lots of pressure, high pressure, because we're very, very close to the pump. Why do I have garden hoses here? Well, I have a house. I live in a house. And we have a basement, and my basement has a pump in it. And there's like a water spigot on the side of the house. And if I hook up the 50-foot hose, I get pretty good pressure. If I hook up the 100-foot hose, not so good, but I can still water the garden. If I hook up the 150-foot hose, I'm going to be waiting a long time to water my garden effectively. And this is because I am getting further and further from the pump. And the same situation is present in the human body. The most difficult for students to understand is an electrical grid. Well, you know what? I can't say that. The most difficult for me to understand and teach you about is an electrical gradient. It's not exactly high to low. It's not like 1 molecule of glucose or a liter of pumping blood. What happens with an electrical gradient is that you have to consider positively charged items. It can be ions, full molecules, right? And our positives here are in orange. And we have to consider negatively charged ions, molecules, and we have to consider their relative abundance. So it's not about the fact that there are lots of positively charged things on the left-hand side of this picture. I don't know how to spell abundance. Here we go. It's about the fact that there are lots of them in relation to these negatively charged ones, right? So it's kind of like the word older. You can't just say Amy's older. You can, but it's better to say Amy is older than Joe, right? So it's a relative term, not an absolute one. Now, ions, molecules, other items, they will flow from where their charge is abundant to where their charge is less common. And so what you're seeing here is that the positives are abundant over here in relationship to the negatives. Over here inside this cell, this big square here is a cell. Over here inside of this cell, we can see that the positives are less common in relationship to the negatives. And so if given the chance, these positive molecules, they'll move right through this little protein right here. It's like a window in a house. If that protein is not there, then this little ion's going to go bloop and bounce right off of it. So even if you have a gradient set up, it doesn't necessarily mean that molecules, ions, and other structures will move. They still have to have the opportunity to flow through a cell membrane, which we discuss in a later chapter.